OK, so here's where we were. So we were talking about this example of beta S gamma and a heavy to light current. So our current, in terms of this chi field, our current was chi. Could have some label, a heavy quark field. And we did the one-loop diagrams in SCT. We saw that after we take into account also the zero-bin contribution, that it breaks up as follows. There's a piece that I've underlined in orange that matches exactly with the IR of QCD. There's a piece that I underlined in blue, which is the ultraviolet divergences in the effective theory. And so what we do with that is we add a counter term for the operators in the effective theory to cancel these divergences. And then there's whatever's left over after doing that, which is this pink. And the difference of the analog pink in the full theory and this pink will give you the matching. So when I say matching, this is part of what goes into that matching. So what I want to spend today's lecture on is really discussing renormalization in the effective theory and summing logarithms in the effective theory. It's kind of interesting and different than things we've encountered before, because we see even at one loop order, we have a 1 over epsilon squared divergence. And that wasn't something that we encountered before, and so we have to see how that plays out. OK, but just at the simplistic level, let's just say, or record for the record, that we could write the following. There was a Wilson coefficient of this operator. And we can divide it into a normalized Wilson coefficient and a counter term. And then we just think that this counter term is canceling that divergence. And so the counter term we need is the following. So with this minus sign canceling that minus sign, you get plus. And so the counter term for the operator, therefore, should have a minus. And just exactly these terms. Because of kinematics in this problem, this omega, which is a delta function in this operator, is equal to actually mb. And I'll go through why that is a little later today. So take it for granted for now. And it comes about just simply from kinematics. But I'm going to sometimes write the mb as omega, because that reminds you that it was kind of this label in the collinear field. OK, so this is the type of counter term we have. It's got this 1 over epsilon squared. It's got this log. So it looks kind of different. And the notation here is that we have a coefficient that's inside an integral. Where this thing meant that. So basically what I'm saying when I say omega is equal to mb is that this delta function becomes omega minus mb. I'll come back to that. OK, so if we have a counter term like that, then we can do running. So we'll come back to this example. Let me first make a few general comments, and then we'll come back and see where this z leads us. So in general, you're going to have this structure. Some integral, some Wilson coefficients that depend on some omegas, could be more than one of them, and then some operator that has some delta functions in it that pick out those omegas. And because of that integral, in general, you have to be careful. Because that integral could also play a role in the renormalization. So that delta function was picking out the total momentum of the product of the quark field times the Wilson line. And in our example, it's fixed by external kinematics. So I'll come back to this and show you that not in every example is it fixed by external kinematics in a minute. But our example is special because the integral actually doesn't play an important role. So there's, in some sense, two parts of this statement. There's the fact that it's external, and then there's the fact that it's fixed to something. So let me first deal with the issue of it being external. And what that means is it does not involve loop momenta. You see, when we did the calculation, we were basically doing a calculation, not worrying so much about this delta function that was sitting inside our operator, right? We kind of ignored it. We didn't write it down in our diagrams. Technically, we should have written that delta function, this delta function down too, and included it in our calculation. But actually, that's OK, because that delta function just comes outside the loop integrals. That's what I want to show you. So does not involve loop momenta. So in all the diagrams we considered, that's trivial except for one non-trivial example. And that non-trivial example is the example where we had a linear vertex type diagram like this. So we called the external momentum here P. This was P plus K, and if I let this guy go this way, we can call it minus K. You see, the Wilson coefficient sits here at the vertex, and it acts on the linear fields that come out of that vertex. But it gives the sum of the momentum of those linear fields. So we get this guy, and then we get this guy, and so we just get the external guy. Okay, and so the Wilson coefficient, so from this notation, it's the same thing as saying this delta function. We can see that it only depends on the external P, not on the n bar dot K. And that's because of kind of the structure of this operator. So that won't always be true. It could be the case that the Wilson, in a more complicated example, that the Wilson coefficient could depend on the K, and then that would have some implications for the renormalization. And we will treat an example of that sort in the near future. The second thing to ask is, what is it fixed to? So if we put a little more into our diagram, let's put the photon in. This is a B quark. This is a strange quark, beta S gamma, for example. Then the kinematics of the external lines there is we have MBV coming in for the B quark, P of the photon, and P of the external strange quark. And the photon is light-like. P gamma squared is 0. And in the setup here, we could just think of it as E gamma times n bar, because P is collinear to the n direction, and it's going, we have the photon going this way, and it's back-to-back with a jet that's described by the collinear n direction. So this is the B meson decaying to a photon in a back-to-back jet. And so if you dot into this equation n bar, since n bar dot v is 1 in kind of conventional coordinates, we just get that mb is 0 plus m bar dot p. And that's the statement that omega was just mb. So when we were doing our loop calculations last time, we kept writing mb. We could have been more careful and written, well, we couldn't have been more careful because kinematics was demanding that this was true. So, but just in order to track what the Wilson coefficients can depend on, really what they can depend on is these labels of these collinear fields. And so I'm going to start writing omega for that reason, because that's the more generic thing that happens, even if we're not in a situation where it's fixed to be some mass. We will get dependence on the values of these parameters omega. OK? So any questions about that? All right, so this Wilson coefficient just comes out, and we didn't have to worry about this delta function. So how do we calculate the anomalous dimension? It's the usual story. So mu d by d mu of the Bayer coefficient is 0. That implies a renormalization group equation for the MS bar coefficient. And it's got this familiar form where the gamma is products of z's and z inverses. Just this. So if we want to plug, so this is an all orders formula. If we plug in our one loop result here, then on the left, if we work to order by order in alpha, on the left-hand side, we can just take the 1 in the ZC inverse here. And the ZC, when we take mu d by d mu, there's mu in the alpha s, and there's mu in this log. And we're going to have to differentiate both of those. So let me write it out. OK, so the minus sign canceled the minus sign. The ZC inverse is just 1. And then I have mu d by d mu of the rest of the stuff, which includes both the alpha and the log mu over W. These are the type of contributions we get. Where these guys here are coming from using the fact that mu d by d mu of alpha when you're in d dimensions is minus 2 epsilon alpha plus order alpha squared terms related to the beta function, which we can drop here. And then this guy comes from the explicit, differentiating the explicit log mu over W. The divergent terms cancel, and we're left with a finite anomalous dimension. And it's got two types of terms in it. So the type of anomalous dimensions that we're used to are like this guy here, this 5 times CF. That would be like a standard anomalous dimension for an operator. In this case, we have this extra piece that has this log of mu over W. And this guy is what's called the cusp anomalous dimension, the guy that multiplies the log. So with that language, you could call this guy the sort of regular anomalous dimension. Now, if you're going to do renormalization group evolution, you're going to sum logs, and you're going to think, you could think that you're starting at some hard scale like W. W was MB, that's the hard scale. And then you want to run down to some small scale mu. When you run down, if you take mu small, this term is larger than this term. Okay, so actually this term here gives you the leading, what are called the leading logs in this case, and this term here is actually only needed for next to leading log. Because this term here grows when you go down and that term doesn't, this term here is actually giving you the leading logs. So I'll come back and talk a little bit more about leading log versus next to leading log, and also I'll explain to you what this word cusp and this, where's the cusp, since we haven't seen it yet. I'll come back and explain where that is in a minute. But now, for now, let's just take the leading log anomalous dimension and just solve the anomalous dimension equation. So we'll just take the leading log term and not worry about the other term. So just taking the cusp term. So plugging that back into our equation for C, we have this differential equation, which we can also write as d log C by d log mu okay? And that's an equation that we can basically just integrate, since there's no C on the right-hand side. It's a homogeneous equation. We can integrate it with some boundary condition. So we could specify the boundary condition at an arbitrary scale. Let me, for simplicity, use the following tree-level boundary condition. So at tree level, the Wilson coefficient was 1, but we have to pick some scale where we make that statement true. And for convenience, I'm just going to take that scale to be W. That makes things a little simpler. In general, you could make this any hard scale, i.e. any scale mu of order W. So you could call it something mu naught and consider the renormalization group from that scale. But for convenience, I'm just taking that mu naught to be W here. Okay, so we take that boundary condition. It's actually useful to look at what would happen if we didn't have a running coupling on the right-hand side. So say we were doing QED and we didn't have any massless light fermions, so there was no running. Then this coupling would just be alpha and it wouldn't run. And then you just integrate this log and you get a double log. You integrate one log by d log, you get log squared. And this is, for each coupling you get log squared. This is the double log series that I kind of promised you, that the Sudakov double logarithms that were going to come out of the renormalization group of SCT. So QED with alpha fixed, you can take CF to be 1. When you take the exponential of what I just said, then this is your result for the Wilson coefficient. And this is what's known as a Sudakov exponential, the leading log Wilson coefficient, leading log. Wilson coefficient is the sum of these alpha times double logs. So if I expanded this out, I'd have an infinite series where for each pair of logarithms, I get one coupling. And that's the Sudakov double logarithms. So if we expand out the exponential, that's what we would get. So really I should make my line go under the whole thing. Okay. So why did we get something like this? So physically, the reason that we got this Sudakov exponential or Sudakov form factor is related to the fact that the whole theory that we've developed put restrictions on radiation. So there was kinematic restrictions put on the radiation by the whole setup that we had. We had this jet, and it was collimated, and the radiation was forced to go inside that jet. In the effective theory, we're seeing this Sudakov exponential come out of UV renormalization. The usual picture for it is that you're thinking about IR divergences, and you're thinking about the real radiation, not the virtual radiation. But as you may be familiar with, what the effective theory does is if you have an IR divergence in full QCD or full QED, then what the effective theory does is it takes the scale corresponding to, so the IR divergences are logarithms, right? And they're logarithms of something over something. And what we've done in the effective theory is we've introduced a scale mu. We've taken the part of that logarithm that was UV and taken it to infinity. And in the standard way, we've introduced a scale mu that sort of splits things between Wilson coefficients and operators. So there's this factorization scale that's splitting the hard physics which is part of the logarithm that we're capturing. It's separating the hard physics from the infrared physics. And here we're just looking at the hard physics, and we can see the Sudakov. We could also look at the real radiation and see the Sudakov by studying real radiation diagrams. But this is, in some sense, this is easier because this is just coming out of a renormalization group equation. So the usual way of doing it would be to just look in the full theory, and you'd see Sudakov logarithms from ratios of two things that you were thinking of as IR, because the hard scale, which is MBW here, would also be an IR scale from the point of view of QCD. But here, it's become part of the Wilson coefficient, and now it can be treated by the renormalization group. OK, so QCD is not really any more complicated. We just have to deal with the running coupling. And we've done that before. Let me remind you how it works, because it's slightly more involved in this case. So for the leading logs, we just need the beta naught term, and we can switch variables from d log to d alpha in this equation here. And so then we have to integrate this thing with respect to d alpha. And so what we can do is we can take this log, and we can also write the log as an integral over alpha. Alpha in this equation is some dummy variable. And so then just integrating both sides of this equation here, I can write it out. OK, so the log became this thing. And then one of these factors, there's a minus sign, but then when I use this formula twice, the minus sign goes away, and I get two of those factors. This is the other measure here from the explicit d log mu. So we could underline things. Half of this guy, all of that guy. D log mu. Other half of this guy and that guy. And then there's this sort of explicit alpha CF over pi, which I've written as CF over pi up front, not this alpha here. Okay, so we do that integral. We do this integral, well, all the integrals are trivial. We do this integral, and then we get integration variable and fixed quantity, and then we do this other integral. We get a solution. Show you what the answer looks like. It's again an exponential because we're solving for log C. Can write it like this. So we're kind of familiar that renormalization group equations, when you have a running coupling, can give you ratios of alphas, right? We saw that when we were running for fermion operators. Here it's just a more complicated function, but it's again a function of that ratio. And this extra kind of structure is coming about just from the running coupling. So the only difference between this and the QED Sudakov is the running coupling. Okay, so if we were to take this now and we were to expand z, we were to say to expand about alpha of w, then we would get logs of mu over w, right? And so what you should think that this z dependence encodes is an infinite series in this exponential. And so the structure of that infinite series, if I was to expand, would be alpha log squared mu over w, alpha squared log cubed, mu over w, etc. Okay, so in the exponent, a running of the coupling is only giving you one log for each alpha. So the series that I'm summing in the exponent by taking into account the running coupling is a series of this form, where I go down by one alpha and down by one log.